Okay, so we were looking at absolute extrema, so absolute max, absolute min. Let's turn our attention now to relative extrema. How are we going to find these? What do they mean? Okay, so relative or local extrema. If there is an open interval containing C on which f of C is a maximum, then f of C is called a relative or local maximum of f. Okay, so it means that if there's some interval around a point which is a maximum over that interval, then it's a relative maximum. Similarly, if there's an open interval containing C on which f of C is a minimum, then f of C is called a relative minimum of f. So let's take a look at this sketch right here. So let's take a look for these absolute and relative extrema. All right, so looks like we have down here, looks like we have, it's definitely a relative min, but since it's also the minimum overall, we'd really kind of default and just call that an absolute min. All right. Up here, we have a relative max. Not absolute because the function keeps going up later on. All right. And then over here, we also have a relative min, a place where it's a minimum right around it. So again, if I took some interval from there to there and just considered that interval, then it would be on that interval a minimum, or in other words, an absolute minimum on that interval. But for the whole function, it's a relative minimum. Okay. There's obviously no absolute maximum because our function keeps going on up to infinity. Now, there is some debate over what to do about endpoints. So if we had something like this, the idea is we definitely have an absolute maximum there. And what do we say about this? Is that a relative maximum? I like to think of it as a relative maximum. A lot of people don't, and in particular, our book does not consider endpoints to be relative extrema. So it is a bit of a lack of convention there. Again, I like to think of them as relative extrema endpoints if they fit the characteristic, but a lot of people don't. So just a note there. Okay, well, graphically, it's clear how we find extrema. But how do we do it analytically? So somebody gives you a function. How do you do it? Well, we're going to start by looking for critical numbers. So these critical numbers, let's define it. Let f be defined at C. So we have a place where the function is defined. Now, if f prime of C is 0, the derivative is 0, or f is not differentiable at C, the derivative doesn't exist, then C is a critical number of f. So two things, the derivative equals 0, or the derivative does not exist. That would make the point a critical number. Now, the function does have to be defined there. So if the derivative doesn't exist, but the function doesn't exist there either, then it's not a critical number. We'll check that out later. All right. Now, the idea is that these are going to be places that help us look for relative extrema. I should make the point that critical number and critical point are often used interchangeably. So critical number would technically refer to the x value at a point if we're talking f of x, And critical point would refer to the coordinates, the x and y value. I'll tend to use them interchangeably. I don't think it's a big deal, but that's how you would see it differently. Okay, so we're talking about the derivative being 0 or the derivative not existing. Okay, that makes sense because if we go back to our graph here, look at the places that we talked about. Here, here, and here. Note that all those places are places where the derivative is 0 or doesn't exist. So in this first one, horizontal tangent line, derivative of 0, horizontal tangent line, derivative of 0. And here we've got that sharp corner, and hence the derivative doesn't exist. So this is leading us to believe that these are kind of the right places to look for. Now, a key fact that I'm going to keep repeating is that being a critical number makes you a candidate to be a relative extrema, but doesn't mean that you definitely are. So we have to remember that. So when we're talking about finding these critical numbers, we're finding candidates. Let me write that. So being a critical number makes that point a candidate to be a relative extrema. But definitely doesn't guarantee that it is. So we're going to have points that have a derivative of 0 or they're not differentiable there, and yet they're not relative extrema. So we have to be careful with that. Okay, so let's just look for some critical numbers, and then we're going to see what we're going to do with it in a minute. Okay, find the critical numbers of f of x equals x squared times x minus 3. All right, so this shouldn't be too bad, because what we're going to do is we're just going to take this function x squared x minus 3. I'm going to be doing derivatives, so I'm going to head and multiply this out, x cubed minus 3x squared. All right, find the first derivative, 3x squared minus 6x. Okay, so again, I found the first derivative. Now I want to entertain the two possibilities. I want to think about f prime of x equaling 0, or f prime of x undefined, specifically where the function is defined. All right, well, equal to 0. Well, 3x squared minus 6x equal to 0, 3x x minus 2 equal to 0, x equals 0, and 2 make the derivative 0. Those are going to be critical numbers. All right, f prime of x undefined. Well, no, f prime of x is a nice polynomial, so there aren't any places, so I'm going to say none from there. Okay, so the critical numbers here, x equals 0 and 2. All right, we're not going to do anything with them yet, but just identified them. All right, now how about critical numbers of f of x equals the square root of 9 minus x squared? Again, let's just take the function. Now I'm going to write it 9 minus x squared to the 1/2 in anticipation of taking derivatives. So 1/2 9 minus x squared to the minus 1/2 times, go inside, chain rule, take the derivative of 9 minus x squared, and then I get minus 2x. So if I simplify this a bit, I get minus 1, the 2's cancel, and instead of saying 9 minus x squared to the minus 1/2, I'm going to write that in the denominator as the square root of 9 minus x squared. Oh, I'm sorry, actually I get an x on the top here. So I have minus x over square root of 9 minus x squared. All right. I don't like how this is. Okay. So now that's the derivative. Okay. So we ask our two questions again. Whoa. Sorry about that. We ask our two questions. When is the derivative equal to 0? And when is the derivative undefined? Well, derivative equal to 0, take a look at this. That would be when x is 0, the numerator would be 0. When's the derivative undefined? Well, it would be undefined when the denominator there is 0, and that would be for x equals -3 and 3. That's what would make 9 minus x squared 0, and hence you get a square root of 0 or 0. Now, those points, realize that this is also needs to be where f is defined. So f is defined at this -3 and 3, because if you look at the original function here, f is perfectly fine there. But it's once I take the derivative, those points became problems for the derivative. So we do get 3 critical numbers here. X equals 0, -3, and 3. All right, so those are all critical numbers. The 0 causing the derivative to be 0, and the -3 and 3 are places where the function was defined, but the derivative was not. Okay, so like I said before, relative extrema only occur at critical numbers, okay, or endpoints. Again, I like to consider the critical numbers, those to be relative extrema at endpoints, so I'm adding that. But not all critical numbers are relative extrema. Just like I said before, being a critical number makes that a candidate for being a relative extrema. But we're going to see that there's a lot more that goes into it.